This section is making use of the iterative prediction method, and I highly recommend that you work through the example on page 105. This is based off of, and my recommendation would be to sit down with the problem and maybe skim through the solution that they have there, and then without looking at the book, try to recreate the steps as best you can. And keep on doing that until you feel comfortable doing that. And so what we're doing is with most real-world situations, we can't actually find a nice analytical solution. We usually have to make approximations. So when we're doing real-world calculations, we usually do something related to this. The things that scientists actually use are, the algorithms are a little bit more complicated, but the idea is really the same. So what you do is to figure out which way something's going and how the path it's going to follow. You just kind of follow these steps. So the first thing you do is you assume that this object comes into this point with some initial momentum. And what we know is that as this object is traveling along its trajectory, we know that in the real world this trajectory would be some sort of arc. We know that as it's traveling along its trajectory, the force is going to be pulling towards the sun, and that is going to have an effect on changing the direction of the momentum. So what we're going to do is, rather than looking at the effect of the force at all of these little points, we're just going to approximate by assuming that whatever that force is at this point is, just assume that that force is constant over this whole path, and that the momentum itself changes right here, right at this point, due to that force. So the first step is, we'll assume that this guy comes in with some P initial, and let me actually call it P0. We're doing multiple steps here. So it comes in with some P0, and again, we know that this object is going to be moving along a path, but we're just going to say, well, if this force were to act right at this instant, what would happen to the momentum? So the first thing we need to do is calculate what this force is at 0. And let's call that F0, and we would go ahead and use negative G m Earth m Sun over the radius at 0. And we're just going to assume that the Sun is at the origin, and it's going to be R0 hat. So that gives us our initial force. And so this P1, which is the momentum heading towards point 1, P1 is equal to P0 plus F0 delta T, where delta T is the time step that we've chosen. And so that's the time for the Earth to travel from this point to this point. Now, we need to calculate the average velocity, and the thing to keep in mind here is that the normal equation we use for average velocity, v1 plus v2 all over 2, is a rough approximation in this case. That equation only gives us an exact answer when the forces are constant. So the thought is that since v1 plus v2 over 2 is inexact, let's make it simple. Let's go with something even easier, and we're just going to use the v final, or v1, as my average. And so that's going to come from P1 over M, assuming that V is much, much less than C, so gamma is approximately 1, and thus P is approximately MV. And then from this, I get to find what my new position is. R1 then is R0 plus this V average. And to be more precise, I should probably call this V average 1, 0. That's the average velocity going between point 0 and 1. 1, 0 times delta T. So I've got a new position. Now what I'm going to do is figure out where this is. So again, what we're doing is we're taking the force at this point, pretending that that force is going to act for a length of time equal to our time step, and we're asking, at this point, what effect would that force have on the momentum? So now I have to do the next thing. This is F1, or F0, P1, F1, P2. So now I've got to calculate F1, negative g, mass of the Earth, mass of the Sun, all over R1 squared times R1 hat. Then we update our momentum, find P2, that's equal to P1 plus F net, I'm sorry, I'm getting my notation confused here, F1 delta T, my V average is approximately equal to V2, which in the low speed approximation is P2 over M. And then finally R2 is equal to R1 plus V average 2-1, which is this guy right here, delta T, and that gives me my next position. And then if we're feeling really ambitious, we could go ahead and just keep on going. And what we would find is just doing the same steps. Find the net force. From the net force, figure out what that new momentum is. From that new momentum, find the average velocity. From the average velocity, find the new position. So hopefully this gives you an overview of what this section is all about. Really, the only way to learn this is to try it out. And if you have any questions, please come talk to me, and I'm more than happy to help you work through some of these problems.